Hello, everyone. Welcome to today's webinar. We'll get started in just a moment here. All right. Hello. Thank you and welcome to today's webinar organized by EERI's Younger Members Committee on Soil and Tsunami Structure Interaction. Before we get started, if you're not familiar with EERI, I just want to take a brief moment to talk about the organization. I'm Elizabeth Angel. I'm EERI's Communications and Program Manager. And if you're not familiar with us, EERI is the leading nonprofit membership organization bringing together professionals from a wide range of disciplines and backgrounds who work together to understand earthquake risk and achieve earthquake resilience in our communities, both here in the US and around the world. So our members include researchers, practitioners, students, who do all kinds of great projects, including the work of the Younger Members Committee. If you're not a member, I encourage you to join us. There's a link there on the slide, and I'll drop one in the chat as well. We'd love to have you become part of these efforts. And our webinar series, you can find out if you're an ER member, you get emails or you'll see them in the Pulse newsletter. You can also check this upcoming event section on the myeri.org website for more information about upcoming webinars. And then you can also check out our webinar recordings after the fact on our YouTube channel there. So this webinar's recording will also be added to that channel in the next week or two if you want to share it with anyone. So on that note, I'll turn it over to our moderator for today, Ken Hudson of Hudson Geotechnics. And before he welcomes the speakers, I just want to remind you briefly that you'll be entering your questions for the speakers today using the Q&A tab on the Zoom control panel. So not the chat, the Q&A tab. Ken will welcome us on behalf of the Younger Members Committee.
Yes, thank you very much, Elizabeth, for that introduction and for doing all the technical pieces of hosting this. We really appreciate that. And thank you, all the participants, for attending today. Just like you all, I'm very excited to be hearing about some of this pioneering research in tsunami and soil structure interactions. So with that, I'd like to introduce our speakers here. We have Dr. Felipe Vicencio and Dr. Rafael Aránguiz. And so Dr. Felipe Vicencio has his PhD in civil engineering from the University of Bristol in the UK. And his research focuses on structure-soil structure interaction, abbreviated SSSI, and seismic effects in dense urban systems, developing three-dimensional numerical models to evaluate these phenomena. He also explores the seismic response of wind turbines and non-structural components, seeking to improve the safety and functionality of critical infrastructure during earthquakes. His studies combine advanced simulations with fundamentals of structural dynamics to better understand seismic amplification and wave propagation in complex environments. And so with that, I think I'll give it over to Felipe to begin, and then I'll introduce Rafael when it comes to his presentation.
Thank you very much, Ken. I wonder if my presentation is look fine.
Yes, it looks correct.
Okay, thank you very much for the presentation. So today I will talk about the key parameters for the study of structural-soil structural interaction. Basically, the work I will show you here is based on reduced order models, which was calibrated in a different ways, like a finite element simulation and experimental campaigns. Also, I will present some results from the Fondesit projects that were working here in the university. And the main goal of this talk is to better understand when neighboring buildings significantly change each other's seismic demands, and how we can capture in the practical analysis. So this is the outline of the talk. I will start first with a brief introduction of the soil structural interaction. Then I will go deep to structural soil structural interaction. Basically, it's a little different because here we start to consider multiple buildings and also some broader concept of city-side effects. After that, I will describe the low fidelity nonlinear model we use here, how they are built, what assumption we make, and which parameters are important. Then the key findings from the projects, and finally, I will discuss with you the future work and urban scale resilience, including where I think this line of research is going. So let me start with soil-structural interaction. So basically, soil-structural interaction is the change in the dynamic response of a structure caused by its interaction with the supporting soil and the foundation system. So basically, in every case, we have this kind of phenomenon. But for some cases, this is not important. For example, for steep or rock sites, these effects are often small, and some codes allow to ignore them. But here we are focused in the case that the soil-structural interaction is important. For example, for soft and intermediate soils. Also, the SSIs can be modeled using different methods, as we will discuss later. The importance of SSIs depends on three different things. The first one is stiffness and mass of the structure, then the of the soils and the damping characteristic of both the soil and the buildings. So basically, this is a figure from the NIST report that I recommended, where they explain very well on which buildings are important to consider the soil-structural interaction, and also they explain the different methods. For example, in the left, you have the direct analysis, where the soil and the structure are modeled all together in one large numerical model. And also, we have the substructural method, which is focused in different steps, where you can consider the kinematic interaction and the inertial effects. But here, we are more interested in the relevance of structural soil-structural interaction. Why is that? In modern cities, buildings are not isolated. Urbanization and current lifestyles have moved population into dense urban centers where structures are separated by just a few meters in some cases and sit on the same soil deposit. So here we can see a great example. This is Santiago de Chile. So we have a large density of buildings where are built very close to each other. During an earthquake, the deformation of the shared soils layer couples the response of neighboring foundations. This is what we call structural soil-structural interaction, or SSI. SSIs can lead to an amplification or reduction of seismic demand. If we extrapolate a pair of buildings to an entire city, we get the idea of city-size interaction. So when we consider the whole city or a very large neighborhood, you are considering the city-size interaction. So why this is important? The first things we need to consider the numerical model, the theoretical numerical model. In this case, we evaluate the SSIs between two nonlinear structures under seismic excitation. Identify the key parameters that govern this complex problem is very important for us. So to answer this question, the key parameters, we can use low fidelity nonlinear model like I show you here. For more details, you can see the paper, Seismic Structure Soil Structural Interaction between Inelastic Structure, where I can show you all the details and all the formulation. So now we have just two buildings interacting each other through the soils. The model is formulated in terms of kinematic and potential energy. The kinematic energy includes the translation of the buildings and the rotation of the foundation. In the case of the potential energy, we consider the nonlinear behavior of the buildings, we also can consider the nonlinear behavior of the soils and also the parameters that include the interaction between these two buildings. To model the nonlinear behavior in this particular case, we model using the Bowen-Sterrisen model. So at the end, we can write the equation of motion for the whole system. The thing is the stiffness between the buildings is not arbitrary. It's divided from simplified analysis expression and then calibrated against more detailed models. Include finite elements and experimental data from the literature. So here I show you one of the calibration using theoretical and numerical analysis. So our aims is try to estimate this kappa parameters, and then we can rewrite the equation of motion. For more details, also you can see this paper that we wrote with Nick Alexander from Bristol. Also, we have to calibrate this interactional spring and these building springs using some experimental campaign. In this case, I show you one particular campaign considering 1, 2, and 3 buildings. But also, you can have a more complicated configuration with different heights, different interbuilding spacing, and different number of buildings. So this is a paper that I'm working right now that is under review, where we calibrate these interactional springs and we compare the seismic response for 1, 9, and 19 buildings. And this is basically our experimental campaign using the shaking table from the Universidad de Santiago. Also, we have to calibrate and compare the response using high-order finite element method. So also, we can show you some works that we are doing here, okay, for asymmetrical building, for isolated building, and different kind of building, because basically you can rewrite and recalibrate this kind of configuration depending of the structural typology and the soil properties. Here, there are some simulation using high-order finite element methods, considering for CLT buildings, so basically cross-laminated timber structure. And the interesting thing that we can see in every of this calibration is the interaction between the buildings are important. Obviously, it's not important for every kind of structure and every kind of soils, but for some particular parameter configuration, this change in the response can be very relevant. So after that, we calibrate our low order model using the experimental campaign and using the high order finite element method. And as we can see, this figure, the red line is the low order model and the blue line is the finite element model. And as we can see, basically we have a perfect match between the two models. So basically we can extract all the complexity of the soils, all the complexity of the structure, and we can model it just using a reduced number of degree of freedom, this large and difficult problem. Then we subject the system to real earthquake records. In this project, we use a different set of earthquakes. considering far field records, near field without pulse record, and near field pulse-like records. These records cover a range of magnitudes, distance, and frequency contexts. And here we can see the variability of all these 100 time histories. Now we can see the different results for different cases and which one are the relevant parameters. First one, to compare the SSI and the triple SI in the meaningful way, we use energy-based metrics. For example, we compute the total power of the displacement and the acceleration responses using the power spectral density and define the percentage change in the response between triple SI and SSI. Why we do that? Because comparing the percentage change in response of the power spectral density, we can get a real understanding of the whole time of the earthquake and not just a simple peak. Also, you can compare a simple peak, but the problem is this kind of things depends so much of the earthquake that you are considering. In this case, a value of 0 means no difference. A positive value indicates an amplification of the response due to the triple SI, and a negative value indicates a beneficial reduction due to the another buildings. We evaluate this metric at the top of each building, considering both displacement and total acceleration, which are directly related to drift and inertial forces. Obviously, you can compare different parameters and different quantity that you are interested in, like a drift ratio or velocity or what you are looking for. So here, a particular parameter set for two neighboring buildings. Building 1, as we can see in the figure, is shorter than the building 2. The red line is the nonlinear behavior, and the blue line is the linear behavior. So first of all, here we compare the displacement and the acceleration, just for the linear and the nonlinear. And then we can compare also between the SSI and the triple SIs, and we can see a change in the response for the nonlinear case in 44%, for the displacement, and in this case of the acceleration, 26%. Remember that is the change through the whole time history. So I think this kind of quantity are very important for this particular parameter sets. Also, we can see what happened with the building 2. So in this case, when we compare the response for the couple and a couple case, we see a reduction of the response. Basically, in some ways, the building 1 shares some earthquake energy between building 2 to building 1. So you have an increase in the energy in the building 1 and a decrease in the energy of the building 2. In this case, the reduction is 34% for the building 2 in the displacement. And in this case of the acceleration, you have a reduction of 25%. And here we can see the difference between nonlinear triple SI and the nonlinear SSIs. And as we can see, you have some amplification because of the interaction between the buildings. When you consider the nonlinear case, it's very important because for some cases, you have a large residual displacement in the buildings. And this residual displacement increases when you have a different building next to each other. And here is some hysteretic curve for building 1 using the Bowen parameters. Now you can analyze these same cases for a million different parameters. Here we have the aspect ratio. Basically, it's the height divided by the width of the building 1 and the frequency ratio between building 1 and building 2. So here, for each these figures, you have 10,000 different points. And for this, every point of set of parameters, you have 100 different non-linear run of time histories. So you can calculate the maximum of the response. Also, you can have the mean and the standard deviation for all these time histories. And the interesting part is for some particular parameter set, you have a large change in the response, a large increase in the acceleration response. This is the case of a displacement anyways. So here I draw the difference, the relative difference between building 1 and building 2. So basically, as a mean, you have 20% of increase in the response for these parameter sets. Also, you can write the same for the acceleration and also doing the same comparison. In this case, you have 40% as a maximum amplification for the 100 records. To move forward to urban scale application, we extend the low fidelity approach to the idealized city blocks. Here, multiple buildings of different heights and stiffnesses are arranged, are coupled through the same soil layers. Each building is still represented by a small number of degrees of freedoms, so the overall models remain computationally efficient. This model shows that the interaction is not only an independent phenomenon that depends of the arrangement of the whole buildings. So here the equation gets a little more difficult, obviously, because you have more buildings. Also, you can have a larger number of degrees of freedom for each buildings, and also you can have more complex nonlinear behavior for the buildings and for the soils. But at the end, you can write the whole equation of motion for the whole system. And also you can write the whole interaction between every building of the system. So in this case, it is possible to calculate the seismic resilience at the city scale. And here we can see some examples, okay? For more details and more examples, you can see the paper that I put here. And in this case, you can see the change in displacement power for all records considered. So for some buildings, you have a reduction of the response, and for some buildings, you have an increase in the response. And these agree very well with all the experimental campaign that we did and I showed you before. So some small conclusion. First, triple size can significantly alter the seismic demand. This is, I think, the most important conclusion of all this study. For realistic ground motion and nonlinear behavior, triple size can amplify displacement and acceleration response by 20 to 30% on average. For some particular cases and for some particular earthquake, 150 to 200% for certain configuration. The most important parameters are the height ratio or the frequency ratio, basically it's the same, between the neighboring buildings, the aspect ratio of the structure, the soil stiffness, and the spacing between the foundation. If you increase the distance between the buildings, all these phenomenon decrease. Shorter buildings, as a general rules, shorter buildings next to taller buildings are particularly vulnerable, especially on soft soils and when the periods are close, like 1.1 when you divide between each other. And also, as a general conclusion, low fidelity nonlinear models are powerful tools. They can simply enough to run extensively parametric study, like millions of different cases, yet rich enough to capture essential interaction mechanics. And now, what we are doing, or what is the future of the research, we are calculate the urban scale application of this phenomenon. So basically, the seismic resilience assessment and the urban scale. So first, what is the different component of this framework? The first thing is choose a city location and find out the portfolio of the building of interest. For example, we're interested in this neighborhood for some reasons. Then we can find out all the properties of every buildings using expert model already published in the literature, the freeware data available in OpenStreetMap, also regional satellite imaging like that using Google Earth or open building datasets. Also, we can use municipality information and tax information. Then we can find out the geotechnical properties of the site. What kind of geotechnical properties are interesting in shear wear velocity and density for every part of the portfolio of buildings. And then we have to simulate different seismic scenario for this particular site. Then we can write the low fidelity model using the framework that I explained before. And using that, we can write the fragility curves, considering the city site effects, and the loss curve, considering the city site effect and the structural solid structural interaction. And the idea is compare both. What happens if you if you draw the fragility curve considering the building as isolation, and then the fragility curve considering the whole city. So basically, this is that we're working now, and I hope that the next year we are running some case study from a city in Italy and a city in Santiago. Thank you very much, and this is my email if you can to share with me and try to collaborate. Thank you very much.
Thank you so much, Felipe. That was really great presentation. And we'll be taking questions at the end. So we will go on to our next presenter, Rafael. Dr. Rafael Aránguiz has his Doctor of Engineering from Waseda Daikaku University of Japan. He specializes in numerical tsunami modeling and coastal resilience, leading applied research in natural disaster risk reduction. He's developed pioneering studies on tsunami structure interaction and impact on critical infrastructure, integrating engineering and risk management. His scientific production and participation in research projects position him as a reference in engineering for resilience to coastal hazards. And with that, go ahead and take it away, Rafael.
Okay, thank you again for the presentation. I hope you are seeing the whole presentation and not the presenter.
Yes, yeah, it looks perfect.
Okay, well, I apologize in advance for my English. I will try to do my best you can understand. The topic today is about tsunami scour around structures, since I've been researching on tsunami. And I will present a very short introduction, motivation, some topic about tsunami engineering, tsunami forces, and then a lot of tsunami, you see, tsunami scour around structures, and short summary of the presentation. Why should we study tsunamis? We know that tsunami are very extreme coastal events generated by earthquake, landslide, volcanic eruptions, among other natural phenomena. In general, earthquake of magnitude larger than 8 can generate this sea bottom deformation and tsunami. And this tsunami propagates, as we can see in the image in the right-hand side. The tsunami propagates as shallow water waves subjected to different phenomena like refraction, diffraction, and shoaling until we have the effect in the coast and on the infrastructure. Why in Chile we are so interested in tsunami? Because as many other countries, we are located along the Ring of Fire. The whole country, the whole Chile is affected by earthquake, as Mexico, the western coast of the United States, Japan, for example, New Zealand. And in Chile, in the map in the right-hand side, we see a timeline and then the longitude along the country and the main events from the arrival of Spaniards. So we can see that we have several events of earthquake and tsunamis, like the one in 2010, 8.8, with a tsunami which reached up to 29 meters in the coast. And we also have the largest recorded event in history, the 1960, which is 9.5, and the earthquake generated a tsunami which affected not only the Chilean coast, but also the entire Pacific Ocean. So that's why we need to understand this phenomenon and design structures against tsunamis. I would say that the key point on tsunami research is the Indian Ocean tsunami in 2004, because this event affected 12 countries and killed more than 300,000 people in these 12 countries. From the engineering point of view, we are interested in tsunami loads, which are often sufficient, large enough to cause the failure of the structure. We also have these floating or structural debris like containers or damaged houses, which can also cause some damage on the structures like projectiles. And of course, we can also have some erosion around the structure called scour, which can also cause failure of the structure, as we can see in the pictures in the right-hand side. So this white building, even though it is not affected by the earthquake, but collapsed due to the scour around the structure. In general, when we are focused on development of tsunami resilient communities, but we have several dimensions, like at least six dimensions, including tsunami hazard, early warning, physical, environmental systems. But we also have governance, institutional policies, tsunami awareness and education, and social ties and community. But when we talk about tsunami engineering, we are more focused on the first three dimensions, especially in the third one related to physical and environmental system, the design against tsunami loads. So when we talk about tsunami engineering, we are talking about the engineering which applies scientific and technical method to design structures, systems, and models that reduce the physical impact of tsunamis. For example, it supports hazard analysis. We need to understand the hazard. We need to quantify the inundation. It is done by numerical simulations, for example. Now we are dealing with deterministic approach or probabilistic approach, which is the return period of the inundation we need to design to. It is still under discussion. For example, in Chile, we don't have many probabilistic maps, for example. It also integrates with early warning systems. We need to design this kind of buildings or structures. We need to design specific buildings, for example, critical infrastructure or tsunami evacuation buildings. When we talk about critical infrastructure, we're also talking about ports, port facilities. They should be in the coastal area. It could not be possible to have a port outside the inundation area, unfortunately. And of course, we also are talking about the governance. For example, setting construction codes or some regulation regarding the location of infrastructures. In the picture, we see some examples of reconstruction after 2011 tsunami in Japan. We can see several layers. This is the multi-layer approach. So we can see seawalls, for example, farm areas, elevated roads, and then we have the buildings. Also, in the lower picture, we have some port infrastructure, then industrial area, tsunami evacuation facilities, and then we have the residential area. So when we're talking about tsunami or strategies to control tsunami impact, we are talking about several layers to control or stop or decrease tsunami energy and subsequently the tsunami impact on the structures. If we want to design structures against tsunami, of course, we have the ASCE standards, 722, the minimum design laws and associated criteria for building and other structures, and we have the specific chapter 6 for tsunami loads and effects. When we are talking about tsunami loads, we are talking about mainly 4 forces. There are other forces, but mainly 4. It is the initial impact force, the impulsive force when the tsunami bore or the first inundation arrived against the structure. Then we have the hydrodynamic force, like the drag force we study in fluid mechanics. Then we have other impact forces due to tsunami debris, containers or rest of structures, damaged structures. And we also have some debris damming. This debris damming against the structure can also generate another impact. So this code is related to all these kind of forces, but the figure here, this diagram, is very important because the hydrodynamic of the tsunami is quite different from the hydrodynamic of a river. In the case of tsunami, the most difficult part to reproduce in laboratory, for example, or to measure on field is the maximum inundation does not take place at the same time of the maximum velocity. In general, when the tsunami inundates an area, we have the inundation and then the maximum inundation with velocity 0. And then the tsunami recede, or we have the return flow and again the maximum velocity. So this is very, very important to have in mind when we are designing the structures. We cannot combine just the maximum velocity and the maximum inundation because they are not happening at the same time. If we do this, we are really, really conservative from the structural point of view. In addition, when we design a structure against a tsunami, we need to consider that if we have a building, a concrete building, for example, like in the figure, we have an earthquake. Before the tsunami in general, we have an earthquake, a large magnitude earthquake, for example, 8.5, 8.8, including magnitude 9, which can cause severe damage to the structure. And then on the damaged structure, we have the tsunami. So we need to analyze the damaged structure with the tsunami loads. And these forces are the drag force, including this scour around the structure. So it's not that simple, we just apply forces. We need to analyze the damaged building with the tsunami forces using these different combination loads. What's the tsunami scour? The tsunami scour is one of the main causes of a structural failure, and we are talking about this erosion around the structure due to the different vortices generated due to the interaction of the flow with the structure. And what is interesting here that when we go to do some field survey after a tsunami, we in general measure this tsunami scour, the scour depth. We have seen some equation based on these measurements, and we can design a structure considering these measurements. But The tsunami survey identified that final scour depth is not the maximum. The maximum can happen during the inundation. And this maximum inundation depth can cause the structure failure, not the final scour. So we will see some analysis in the coming slides. In a recent paper we just published, we performed some experimental analysis in the lab, combining with a numerical simulation using dual physics. So we have this 20 meters long waveflume. We generated a solitary wave, and on the other side we have a beach, the slope 1 to 20, and a square structure like a building. And inside we used some endoscopic camera with some mirror in order to observe the scour around the structure. So we performed some experiments. Here we can see the solitary wave, and now we have the slow motion of this wave arriving to the coast and impacting the structure. In the upper part, we have different views of the cameras, the top view, the side view, and the camera inside. So on the right-hand side, we see the camera inside. So we can see the maximum scour, and then when the return flow, there is a small slumping of sediment into the hole. We combine these results, the black triangle with the red triangle here, with many other research. So we see that the larger the flow depth compared to the size of the structure, the larger the scour depth, the normalized scour depth. However, we are only talking about solitary wave of dam break. The solitary wave does not really represent a tsunami wave. When we study tsunamis in laboratory, we can generate these tsunami waves. We can use the dam break system, or recently some people have been using this pneumatic system, so a controlled volume of water in order to generate longer waves. But still we have some limitation regarding the hydrodynamic variables and the return flow. So what I did in my lab was to generate a new system with pumps and gates to generate a flow similar to a tsunami in the coastal area, controlling this velocity and the inundation depth. So as I said before, the maximum inundation does not take place at the same time of the maximum velocity. So I try to reproduce the variables in this wave flume. So we have the pump, we have a flow straightener, we have the central part with sediment and the column. Here we have some images of the camera inside with the mirrors and these emerging gates to control the flow depth. So with the pumps, I control the discharge. With the gate, I control the flow depth and velocity in the central part, which is the area of interest. Here I have some measurements. So the sinusoidal wave, I can simulate the inundation and then the return flow, and the velocity during the inundation and the velocity during the return flow, which give very, very good results. Regarding the scour, what we can see is here we have the inundation, only the inundation phase, the velocity, the momentum, and in the lower part we see the scour evolution as a function of the time. So we demonstrate here, or we found that it was real that the maximum scour is during the maximum velocity and not during the maximum inundation. Actually, when we have the maximum inundation, the velocity is 0. And then we have the final scour. In the central panel, we see some snapshots of the camera inside the column. So the upper part is the front side of the column. So the tsunami scour is increasing as the time increase as well, and then we have the maximum at 29 seconds, and then we have some slumping and decrease the scour. In the rear part of the column, we have some scour in the corner, but then we have an accumulation in the rear side. So we can see this effect here, for example, in the figure A and B. So there is a scour around the structure and then accumulation in the backside, and also here we see the accumulation. But when we have the return flow, the pattern changed a little bit, and now we have the accumulation in the other side, in the front side. And when we have many waves, actually this system, I can generate many waves. I simulated up to 3 tsunami waves. We have like different layers of scours, and every time the scour is deeper and deeper. This is one of the final results. We just submitted a paper with these experiments. So here we have the 3 tsunami waves, the tsunami train, 3 waves. This is just an experiment, so we simulated 3 waves. In reality, we could have many waves, but not all of them are the same height. But in this laboratory case, we analyzed 3 similar waves. And this figure, the lower figure shows the evolution of the scar in the front side in blue and the rear side in red. The corner is the continuous line, and the center is the continuous line, and the corner is the dashed line. So in general, what we see, the front side is the tsunami arrived, we have a increased scour, the maximum, and then some slumping, the equilibrium scour, and then the return flow, and then the scour change. There is an accumulation in the front side, and then another wave, a scour again. But what is really interesting here is every time we have another wave, the maximum scour is increasing. So the tsunami not only increased due to the tsunami wave, but the larger the number of tsunami waves, the larger the scour. So here we have now the new comparison of the previous research. These graphs are the previous research with solitary wave. But with this new system, we have different experiment because we have the same magnitude or the same inundation depth, but we have longer inundation. So due to the longer inundation, we have larger scour depth. So when we include this inundation time in the equation, we have another correlation with the Kc number, the Q ligand and Compton number, which include the velocity, the period, and the size of the structure. So with this research, we have a more closer insight into the tsunami scour and the effect of multiple waves and the effect of the tsunami period, for example. So as a conclusion, I could mention that tsunami engineering is crucial but partial component of tsunami resilience. Don't forget the social parts. Even though we are engineer, we need to deal also with the social side of the resilience. Tsunami engineering and tsunami research include field survey. Yeah, this is for me is quite exciting. We can do field survey, we can do numerical models, and we can also do laboratory experiments. So it means a lot of fun. And tsunami simulation in laboratory is very challenging due to this complexity of the inundation, maximum velocity. And finally, the tsunami scour is one of the most important failure, and we need to do more research in laboratory and numerical models, for example. If you want to know more about tsunamis, I invite you to visit my Instagram, Rafa Tsunami, or if you would like to study a PhD in engineering with focus in resilience, you can also get in touch and ask more about this program. Okay, thank you.
Great, thank you very much, Rafael. That was a really great presentation, and we're going to open up our Q&A little panel session now. And so we're going to go ahead and start with a couple of questions for Felipe on your presentation. So we had one in the chat that didn't show up in the Q&A, but I'll go ahead and ask you right now. And Manji, I wanted to know, in those SSI investigations, did you account for influence of deep basement embedment in high-rise structures? Do you think the seismic response will be different for different basement configurations and things like radiation damping?
Great. Thank you very much for this question. Very interesting. The thing, the results that I show you don't take account above deep foundation. Nevertheless, different researchers are focused in the same topic, and they are doing a lot of research trying to find out the springs that model soil foundation in the way that you can consider the interaction between the buildings considering this depth foundation. And the interesting thing is that this phenomenon for some particular scenario is already important. I can share, if you write an email, this work, and you can see some very good result about this topic.
Great. Thank you. We had another question, and this one is in the Q&A from Maria asking, what software were you using for your nonlinear SSI studies? And how much computation time per time history analysis did it take? Sorry, there's a lot of pieces to this question here, but those are the first two parts. Then, did you try a frequency domain type of linear analysis? And I guess the next question is also part of the previous, are all the buildings at surface elevation? It sounds like, yes, there's no basement embedment effects, but you can also elaborate on that. And how is this study going to be applicable for future design standards and codes?
Well, thank you, Maria, for those interesting questions. The first one about for the reduced order model. In the beginning, we use MATLAB. So basically, you can write all the question in MATLAB, and then we move all the formulation to OpenSys for the lower order model. For the high order model, for the high fidelity finite element method, we use ANSYS for the results that I showed you in the presentation before. Regarding the time that it takes for the lower order model, basically it takes like 90 seconds for each run. So it's very quick for the non-linear case. In the case for the high fidelity finite element models, it take like 2 days for run a complete fully non-linear model. So basically, it's a big difference between the reduced model and the high fidelity models. And this is for just 2 buildings. So when you start to consider it like hundreds of buildings, obviously the time increases exponentially, especially in the high order modeling. Regarding to the frequency domain, yes, we already do the comparison in the time domain and the frequency domain. Generally, we get pretty much the same response, but when the kinematic effect starts to go important, both results start to be a little more different. And finally, about if this investigation is applicable to standard and code, this is our final idea. Is try to recommend some simple, for example, recommendation. For example, if you have a lot of building each other and you have to build a new buildings, consider the same demand from the earthquake, but increase something like 20% But obviously, we have to go deeper in this research and try to find out some final conclusion to get for standards. So yeah.
Great. Thank you. And I personally have a question for you too that I'd like to add to this. So when you're doing these nonlinear analyses, are you only considering nonlinearity in structural components, or are you also considering nonlinearity of the soil? And if so, in the bigger finite element models, are you using some kind of constitutive model, or are you just using some kind of a spring parameter for the soil?
In the case of the reducer of the model, we already consider the nonlinear behavior of the soil, but basically it's like a nonlinear springs.
Right. Okay.
Yeah, so we can change the shear modulus depending of the strain of the soils. And the interesting thing, if you consider that, the interaction increases because you soften the soils. In the case for the high fidelity finite element model, we already considered the nonlinear behavior, but here you can have more complex constitutive for the soils. The problem when you get nonlinear in the soil and nonlinear in the buildings, the time running gets very very demanding, like 4 days for one earthquake and one case.
Great. Thanks. So we've got one more question in the chat while you're talking for you, Felipe, and then we'll move on to Rafael. But the last question here is, have you used the domain reduction method as a comparison in your work?
Yeah, good question. No, in my case, not, but I'm aware that different research groups are doing this kind of approximation, but not in my case.
Okay, thank you. We'll go on to 3 questions for Rafael here. First, the scour depends on the type of soil, right? It's kind of a question, but I think intuitively we understand it should be. So what kind of soil did you use in those lab experiments?
Yeah, I'm sorry, I did not mention that, but I used sand, a fine sand. It's 0.5 millimeters the diameter, and all the results in this research I showed, I used different size, but mainly sand and granular soil. We haven't done any research on cohesive soil. But when you use very fine sand in the lab, it behaves as a cohesive soil. So that's why we cannot use very fine sand. But in general, it's from 0.1 to 0.5 millimeters, the medium grain size.
Great, thank you. So your results of the multiple scour patterns are really interesting. Has anyone in this field identified or described these multiple scour patterns in previous tsunamis?
Well, to identify this on field survey is very difficult. We know that we could have several tsunami waves, but we don't know the final results around due to scour is due to the first wave, the largest wave, or the summation of all the waves. So that's why we're doing this research on the lab. So we just submitted the papers suggesting this. When we design something, we need to consider several waves. This is what we propose.
Great. And we have a couple of questions about the numerical modeling as well. When you're scaling the model up to a full-size structure, how does that influence the behavior? And was the sand material modeled in dual S physics? What's your runtime for that kind of a model?
There are several questions in one. Well, actually, we haven't run a full-scale simulation. This is ongoing work. First, we need to validate the numerical model with the scour and the small scale, and then try to run some real scale simulation. So it is ongoing work. We did this before in a previous research, but without the soil. So I'm talking about the soil. We need to do this in the near future. How we model the sand? Here, dual physics has this ability to use the different phases or two phases fluid. One is Newtonian, like the water, and the sand is modeled as a non-Newtonian fluid with a rheological model. So when the bed friction, the stress increase over a critical value, then the sand start moving. So this is the general way we simulate the sand. But then, well, I can explain more details, but in general, this is the way.
Okay, great. Thank you for that.
And I think the last question was about the time, runtime.
Yeah,
So
runtime.
it depends on the size of the model and the amount of particles. The smaller the particle you consider, of course, is the longer the time you need. But when we consider this wavefront of 20 meters with the slope, we are talking about 1 hour, a couple of hours, no more than that.
Great, great. We got a couple last questions now for Felipe that came in just now. If we can flip back over to you. And one, I think this is a really good question. Kevin is asking, when you're practicing structural engineer, when do you discuss the SSSI with a geotechnical engineer? And is there a rule of thumb, like distance between buildings, where this interaction is important?
Yes, as a rule of thumb, when the distance between the building is 2 times the width of the buildings, the interaction is almost zero. So basically, if you have a large street and a square or something like that, it's not necessary to worry about this interaction. But if the distance is closer, like 1 width or less, this phenomenon is important. And when is the right moment to discuss? I think when you start to plan the project, I think you can try to run this kind of low order model that are very quick and try to get a sense of how important is this phenomenon for the new buildings and for the buildings already existed. So then you can take a decision about if it's necessary, I don't know, to propose some proposal about this effect.
Great, thanks. And one more for Rafael here. Francisco is asking, sand is prone to scour if it's not cemented, correct?
Yeah, of course. We are talking about the foundation soil, mainly granular soil. Of course, you can cover with the concrete everything, but we are talking about the sand. Yeah.
Thank you. I think that'll bring us to the end here. I'll hand it back over to Elizabeth.
Great. Thank you so much for both to our speakers for those excellent presentations and to everyone who joined us today and for all those great questions. Just a couple final notes here. You're going to see a survey pop up in the Zoom window when it ends. You also get that by email tomorrow, and we really appreciate your feedback on these events so we can continue to present webinars that are of interest to our community. You can learn more about EERI at our website, and if you're not a member, we encourage you to join us today. As I mentioned earlier, you can check the My EERI upcoming events tab for news about future webinars. And also, yesterday was Giving Tuesday. It's that time of year. And if you want to support this work, you can donate to EERI and to our Learning from Earthquakes endowment, which specifically supports our post-earthquake reconnaissance efforts. And then finally, I just wanted to acknowledge and thank the funding from a cooperative agreement from FEMA, which makes this webinar series possible, as does the support from EERI members like yourselves. Thank you so much. This might be our last webinar for 2025, but we'll see you again early next year. We're already getting a great lineup in order, and you'll hear more about those in the upcoming issues of the Pulse.